Hey everyone, today we're going to look at a couple examples about a particular type of discrete random variable which is known as a binomial random variable. We've actually had some experience with something that might qualify as a binomial random variable. We looked at an example where you play roulette, and a roulette wheel has 38 slots. 2 of them are green, 0 and double 0, and you can see those here. And then the other 36 slots, which are labeled 1 through 36, they alternate red and black. So you can play roulette as many times as you want, and you can make all sorts of bets, but for this example I want to suppose we play 5 times, and each time you're going to bet on red. Okay, so in this case, notice that as far as you're concerned, every single time you play each trial, you're either going to win or lose. Each trial has the same probability of winning and losing, of course, right? So each time if you make the same bet, you have the same chance of winning. And trials are independent, right? Because whether you win or lose on the first trial, it doesn't actually affect your probability of winning or losing on any subsequent trials. So let's say that you're going to play this 5 times, you're going to bet on red each time. I want to know what's the probability that you win none of those 5 times. So we have some experience with probability. Winning no times, so the probability of 0 wins. That would be the probability that you lose your first, you lose your second, you lose your third, you lose your fourth, and you lose your fifth as well. And this is an and probability, right? First and second and third. And since these events are all independent, then we know that we can just multiply straight across the 5 probabilities. Each time you play, the probability of losing would be 20 out of 38 because there's 18 red slots. So that'd be a probability of winning would be 18 out of 38. So the complement would be the probability of losing is 20 out of 38, and that's just 20 out of 38 to the 5th, which would come out to about a 4% chance. Now, this example is pretty straightforward because you can only lose all of your bets one way. You have to lose every single bet. So what happens though, if I'm interested in an event that you could lose, not all wins or not all losses. So what if I want to know what's the probability that you win 2 of the 5 times? So you're going to play 5 times. I want you to win 2 of them. You could think of that as 5 little slots here, right? So you could win, lose, lose, lose. And we know the probabilities of each of these happening, right? So that would be 18 out of 38, 18 out of 38. And then the losses are 20 out of 38, 20 out of 38, 20 out of 38. And they're all independent. So we could just multiply that together, and that'd be about a 3% chance. But something we're forgetting here, if we just did it this way and we use this as our answer, 3%, we're forgetting that this is only one way that you could possibly see 2 wins and 3 losses, because it's not necessarily the case that you have to win the first 2 and then lose the last 3. There's a lot of other ways this could happen. So we need to kind of investigate, all right, well, how many ways could that possibly happen? So you could think of it as in a table, right? So how many ways could the 2 wins, 3 losses happen? Well, it could happen like we showed, right, where there's 2 wins, 3 losses. Of course, maybe you win the first time and then lose and then win with 2 losses. And there's all sorts of possibilities, all the way up to the point where maybe you win the first 3 and you lose the last 2. Okay, so how many possibilities are there total? Well, this is really just a counting problem. So you have 5 slots and you want to see 2 losses, right? So there's going to be 5C2. That's 10 ways it could happen, and all of them are equally likely. But when we're talking about the probability of losing 2 out of 5, we need to include all those possibilities in our probability calculations. So here's the answer we had in the last slide. This is the probability of a single outcome. So 2 wins with a probability of 18 out of 38, 3 wins with a probability of 20 out of 38. But now we need to multiply that by 5C2 because that's the number of ways that we can actually realize 2 wins out of 5. So the final answer would actually be 32%, or actually closer to 33%, but 0.3271. Okay? Now, this example where we had multiple trials that were win-lose, they all have the same probability. This is a very special type of variable. This is what we call a binomial random variable. So for a binomial random variable, you have to have these 4 conditions are met. You have to have a fixed number of trials. So like in our example, we were only playing 5 times. Each trial has to have only 2 possible outcomes. Typically, we think those as success fail or win lose. And then the probability of success has to be the same on each trial. So that's like when we're playing roulette. The probability of winning doesn't change. And then trials have to be independent. That means probability of one, or the outcome of one, can't affect the probability of another. And then if you measure the variable x to be the number of successes out of n trials, or the number of wins, then that x is a binomial random variable, and we say that there's n trials, probability of success p. Okay, and we saw this example here. We kind of came up with this formula where it was a combination times a probability to a power times a probability to a power, and actually that pattern holds for all binomial random variables. So there's something called the binomial formula, and it turns out if you have a binomial random variable with n trials and the probability of success is p, then you can calculate the probability of x successes out of n trials with the binomial formula, which looks like this. So this is number of trials, combination, how many wins or successes, probability to the number of successes, 1 minus the probability to the number of failures, which will be n minus x. Okay, so we can use this formula to kind of shortcut our probability calculations if we recognize the variable as binomial. So if we go back to our example where we were playing roulette 5 times, let's say this time we're not betting on red, maybe we bet on green. So what would be the probability of winning one of the 5 times you bet on green? So first we need to make sure that this is a binomial random variable. So there's a fixed number of trials. We decided we're playing 5 times. The probability of success is going to be the same on each trial because you're betting on green. Thanks. Appreciate it, Jesse. And then trials are independent because each time you bet, it doesn't change the probability of winning. And each trial has 2 outcomes. You either win or you lose. So this is a binomial random variable where n is 5, p is 2 out of 38, and then in this case, x we're going to call 1 because we want to see 1 success out of the 5. So then we'll take the binomial formula from the last slide, like this, and we're going to start dropping in. So everywhere I see an n, I'll put in a 5. Everywhere I see a p, I'll put in a 2 out of 38, and everywhere I see an x, I'll drop a 1. Right? So we got 5c1, 2 out of 38, that's the probability of winning, to the 1, because we want to see 1 wins. 1 minus 2 out of 38 to the 5 minus 1, which that's going to simplify. So that 1 minus 2 out of 38, if the probability of winning is 2 out of 38, then the probability of losing would be 36 out of 38. And notice these numbers match up, right? So these 2 probabilities add up to 1 because they're complement probabilities, and these 2 numbers here add up to the number of trials because if you're going to see 1 win, you have to see 4 losses. And then there's this counting component. And if you calculate that out, you should be able to come up with the correct answer, which is about 21% or 0.2120. So this is how we use the binomial formula to calculate probabilities once we recognize that random variables have a binomial distribution. All right. The other thing we mentioned back when we first started talking about distributions, and we actually talked about this in 6.1, is oftentimes we're interested in the mean and standard deviation. The nice thing about binomial random variables is that you don't need to have the whole table available. You can actually calculate means and standard deviations of binomial random variables. You can shortcut. The mean of a binomial is always going to be the number of trials times the probability of success, and the standard deviation will always be the square root of the number of trials times probability of success times probability of failure. All right. So we can return to our example and we can see this here. It says, suppose you play roulette 5 times. Each time you bet on green. How many times should you expect to win? What's the standard deviation of your numbers of wins? One thing to remember here is right here. Oh, thought I had my pen on. One thing to remember is expectation is synonymous with average or mean when we're talking about random variables. So essentially what we're asking here is how many times should you expect to win? That's saying what's the mean, what's the average, and then standard deviation. But we already know that this is a binomial random variable, so we know that we can use this formula for the mean. So the mean is going to be the number of trials times the probability of success. Well, we're playing the game 5 times. The probability of winning was 2 out of 38. So then the mean is 0.2632. So you'd expect to win less than 1 time if you're playing 5 rounds betting on green. That's your expectation. And then the standard deviation, because it's binomial, we can shortcut, use this formula. Just plug in 5 trials, probability of success, 1 minus p's probability of failure, and then that'll come out to a 0.499. Okay. So gambling, obviously these are independent trials because every time you play, it's like you've never played before. Another application where we treated things as independent is when we were calculating probabilities sampling from large populations. So I'll give you an example. This one talks about on-time flights. So in 2016, Delta Airlines, they had the highest percentage of on-time flights among U.S. carriers, and the percent of the time they were on time was 86.5%, so pretty good. So what I want to know is, let's suppose you take a round-trip vacation, and on this vacation you have to take 6 flights. So if you have to take 6 flights, what's the probability that at least one flight is going to be delayed, right? At first this might not seem like a binomial random variable, but when we really start to think about the requirements, right? So are there a fixed number of trials? And I'd say, yeah, there's 6 flights, right? Are trials independent? Does being on time affect the probability of the next one being on time? And that's typically independent. Those typically don't affect each other unless there was some sort of like weather event, but we're going to assume they're independent. The probability of each one being on time is the same. And each flight is a success-fail, right? They're either on time or they're not. So we can actually solve this problem by doing treating it as a binomial random variable. Okay, so let's think about this, right? So if you're taking 6 flights, let's think about what are the possibilities, right? So as far as the number of delayed flights could be, you could have no delays. You could have 1 flight delayed, 2 flights, 3 flights, 4 flights, all the way up to the point where, I mean, potentially all 6 of your flights could be delayed, and that would be unfortunate, but it could happen. Okay, so we could give these like a letter, right? So this is what we're actually interested in, is this event A. We want to know A is the event at least 1 flight is delayed. That's what we're really interested in. And I'm going to put the complement here because remember, sometimes the complement's easier to calculate. So if A is the event that at least 1 flight is delayed, then A complement would be that none are delayed. And remember that the probability of being on time is 0.865, and the probability of being that means the probability of being delayed must be 13.5%, I think, right? So I think I mislabeled this. This isn't actually the probability of A or the probability of A complement. This is just, sorry, my handwriting is going to be terrible. I'm doing it. This is just the on-time probability. Ooh, it's terrible, but you get it. And then so this must be the delayed probability. I really need to get myself a little, stylus here. But anyways, so 86.5% are on time, so 13.5% are delayed. Anyways, that's important because we're going to need those probabilities here in just a second. So, all right. So if you look at our little chart over here, okay, if you look at our little chart over here, so at least 1 flight delayed, that's what we want to see. Well, that's all of these possible outcomes, right? 1 through 6, at least 1 delayed. But that's a lot of outcomes. If we wanted to do it this way, we would have to use the binomial formula 1, 2, 3, 6 times. But notice, what is the complement? The complement is a single event, right? Just the probability of none being delayed, and that's going to be a lot easier to calculate. So our strategy here is we're just going to calculate this one, the probability of A complement. That's going to be a lot simpler. So the probability of our complement, that's just the probability of none of them being delayed, And since we're talking about delay, we're going to use the delayed probability. So the probability that none of them are delayed, that would be 6 flights, you want none of them delayed. This is the probability of being delayed to the 0 times 1 minus the probability delayed is 6 minus 0. Right, so this is 6 flights, none of them delayed. Probability of being delayed to the 0, because we want no delays. Probability of on time, that would mean 6 were on time. That's a pretty easy calculation. You should be able to get that as 0.4189, about 42%. But that's not actually what we're interested in. This is the complement. This is a probability that none of them are delayed. I want to know what's the probability that at least one flight is delayed. But we can use the complement rule because the probability of an event is just 1 minus its complement. So we can just take that 0.4189 away from 1, and we'll see that the final answer is 0.5811.